Morning. And let me pop up. So I'm just getting up our calendar as well. Let's get it up. All right. 3255. Oh my god. Everything like Chrome has updates, Blackboard has updates. It's like, do they expect me to read that when I'm just trying to get to the software? All right, so goal is for tomorrow, finish up, turn in homework number 4. So last like required homework for the semester. And then next week, I think I'll push off that project 4 to like, I mean, we could push it off till Friday because like we have time. The main thing is just like get it in and then revising previous work or starting to work on module 5. So if you're on schedule, then just get project 4 done. But one of the reasons for that is that on Friday, so this 15th, this thing's in our way. The 15th coming up, we won't have class. We won't have anything in person this coming Friday. There's an all-day like career conference here at UConn, so I'll be there for that one. But, yep, that's the main logistics. Let's wrap up homework 4, and then on Monday we'll come back and take a look at project 4. So we'll give you like Friday or whenever you want to kind of look at that. Monday morning, frantically at 9 a.m., 5 minutes before we start, maybe. Yeah. The old college effort. Cool. How is anything like interesting or questions or concepts to take a look at for homework 4 or module 4, like in general? Or even a step back of like, what is computational mechanics? What are we doing here? Yeah. Yeah. Yep. Okay. Yep. Like when we, oh no, we're not up to that yet. It's all connected though. I just got the one where I'm plotting like 2 different graphs. Oh yeah. So I'm just like running through everything, getting down to like this is the first matrix where when we try to solve it, if we don't do any pivoting, that we run into a problem with like Gauss naive and that LU naive. Like just doing Gauss elimination just doesn't work because I can't take that 0 in row 1, column 1. I can't add that to the next row by multiplying by any factor. And all right, so let's grab. Right now I had already rearranged this, but let's put it back. So if this is my A matrix, there's a 0 in that first column, first row. I can look at LU of A, and it gives me 3 outputs. And the very first one is a pivoting step, so it's showing me how this SciPy linear algebra would rearrange the rows. And it did the same thing that I had done. It took row 1 and switched it with row 2. That's what this, like, those two ones that are, if it didn't switch any rows, it would just be ones all along the diagonal. But it took those two rows and switched them. It also took row 4 and row 6 and flip-flop those. You'll get, if you don't do that, you'll probably get the same answer, but it tries to like minimize how much error it'll think will accumulate during the solution. Yeah, but that's our pivoting. And in practice, what we can do with that is if we have P, L, U, and a right-hand side B. So I want this one. Like with this solve LU, if I want to give it LU and P, the P gets multiplied by B, that right-hand side vector. Otherwise, if I don't do that, then I didn't rearrange like the right-hand side equations. So those all end up getting flip-flopped around.
So the difference between this problem and the one with the triangle one coming down on top, that one's just a regular decomposition. So when you run that, you don't need a pivot because the ones are already in diagonal.
Oh yeah, so if we take a look at like this first matrix where there's a lot more symmetry because theta is 0, so the force is pointing directly down. So yeah, when everything's lined up, it's a little easier to solve. Just 3 equations, 3 unknowns. And if I try to do that LU, or when I do that LU decomposition, really, if I want to use that LU solve, I would still need to take P transpose times B, but P transpose of ones along the diagonal is still just ones along the diagonal, the identity matrix. Yeah, like in this case, if I want to say, what was it? LU solve? No. Sorted? No. Oh my god. I thought it was solve LU. Solve LU. Yeah. Oh, I didn't import it. I didn't run it yet. That's why it wasn't working. Come back up. There we go. And I guess just the other thing, this is equivalent to saying like linalg solve of because inside that solve LU function is the first step of saying lower matrix times the lower matrix times y equals that B matrix, and then the next one is the upper matrix times y equals x, like the actual thing that we're trying to solve for. So it does take ax equals b, split it up into two problems, but both problems are a lot easier to solve than the original if we have the LU decomposition, which we can get. We can get it. And if we're going to reuse the solution, then it's worth doing.
Yeah.
Start the project.
Okay. Yeah.
So if we're talking about a condition, this is a configuration between one, you take out, start with what's the condition of the matrix, K matrix, and you say what's the condition you take out a few of these rows and columns.
Yeah.
So I understand when we're spitting out the condition of the unchanged matrix is 10 to the 16.
Okay.
So then your accuracy is going to be 10 to the 16, 16. So
Yeah.
the question you have maximum use eliminate those your condition 52.7, which is 5 times 10 to the first.
Yeah.
Or so. Yeah. But in here, this was given this whole statement here. This was given as 10 to the 2 minus 16. Is it 10? 5 times 10 squared. Wouldn't it be 5 times 10 to the first?
Yeah.
Okay, it should be. Okay, okay, just making sure. Yeah. I understood that. Okay.
Okay.
Yeah.
Yeah. Yeah.
Seems interesting compared to the other one.
Yeah.
But I'm wondering, so Oh, because I'm just going to use this as before we have that.
Oh, I see. Yeah, you did pivot it, but then you're using LU to get lower number. And that will always be giving you if you use like a naive LU decomposition, then that one it won't pivot.
So I basically.
Yeah. Oh. Just leave it at that one. Or that out. That one, like, bigger condition would be bigger hair. And like the yeah, those would be add that Yeah. And now at the end of homework 5, yeah. This happens. Yeah, it was like project 2. Yeah, exactly. Cool. So you're done with number 4? I'm done with number 4. Okay. But yeah, I was looking for this, yeah. Okay. You know, we will have to take. Yeah. 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 Sometimes that.
So, moving on to the next number 1, set of course. That is number 4. So, we're creating a matrix, K matrix, so we're chopping out some rows and columns.
Yeah.
Then it talks about your apparatus, at number 4. Is this in reference to all the not using truncated force array?
Yeah.
So is that 5 index, is that 5th index for the truncated array or for the original one for the truncated?
For the truncated. Yeah.
Okay. Yeah. So there's only really 11 force vectors from because originally there were 14, we chopped out 3.
Yeah.
So this is the 5th index of 11. Or vector of 11 values.
Yeah.
Okay. Yeah.
Yeah. To kind of double check, like every node has some X and Y.
If you visualize the array for the because it's small KU equals all the so NU has X and Y displacements.
Yes.
So the K is originally 14 by 14 because there's 14 segments.
Mm-hmm.
Does that mean how do I know what row corresponds to X? Because usually U is for solving for X. How do I know which one is X, which one is Y?
That one it goes back and forth. So like the first 2 rows are node 1 and 2.
Which one is first?
Y?
Okay, so XY1 or X1, Y1, X2, Y2.
Yeah.
X3, Y3. Yeah. Okay, so it's the U vector is still going at 14. It's a 14 value vector.
Yeah.
Okay. Because then when you do that product, it just multiplies to get to a value.
Yeah.
For each one.
It's kind of Right. Like if we just had
read two values for each.
yeah, 1 x 2 x 3. Oh, so
U one
sorry, 1
one.
sorry, 1 2 x 2 2 3 x 3 x. Some of them we know, like this one you're saying, that is 0.
So the x direction. Okay, so U0, I see that U1 is also 0. So
Yeah.
U1 displacement is 0 in the x point.
Yeah, so x, this is 0, that is 0.
Okay, and the final one, U13, is also 0. So that's the y direction at the last node. 0 displacement.
So it turns out that we have like 2 unknown forces on the right hand side. And then here, let's say we know this is the triangle. So maybe I also say that 3 is also 0, but with an unknown force there.
Gotcha. So when I'm building this new force, there is no force vector created to start this problem. So basically, create it and you go something along the lines of zeros and 11 done, but then you go 5. So now here's your new vector.
Yeah.
And then
So like when we define those 11 force vectors, those are all the known forces. So like in this case here, let's say force here, I know that it's 0 at 2x, and negative f, it's a 2y, but 0 at 3x.
0 everywhere else. So we can chopped out the top 2 and the last one.
Yeah.
So we know all the forces.
Yeah.
Okay, so basically originally saying we don't know these forces at the unknown node. So getting rid of those, we can now solve for the remaining displacements at those nodes.
Yeah, we can solve for these displacements. And then once we have those, now we can say
3 equations, 3 unknowns, basically, right?
yeah, so that'll give us like 3 equations, 3 unknowns.
That'll solve for all those. Then we can plug them back in, right?
Yeah, to figure out like what are those reaction forces. Okay. So you end up like segmenting the final element problem. Like first 2, what are the unknown displacements? And then you plug those all the known displacements back in and figure out what are my unknown reaction forces.
So next, plug in the U values into the equation. So basically, we use the LU decomposition to solve for y.
Yep.
Y is going to give all those values. No.
Yeah.
And then that gets plugged in to the new U matrix, basically.
Yeah. Okay. Yeah. So like this is kind of like my new free, like everything that's free to move is in there.
And then so instead, this next part, once we know those missing U values, instead of doing this truncated K matrix, we do the full one.
Yeah, so now I can say K times that equals, and really it'll redefine this F, but that's what I mean. So R1x, R1y, 0, and make that 0, R3, y.
Yep. Okay. And then to solve for the backwards and forward substitution for the Ly and UU, can I just do, instead of using the full definition or the full function here, we do a much simpler version where it's now that's all.
Yeah.
We can do a truncated version of that.
Yeah.
Okay. Yeah. All right, that makes sense.
Yeah.
Thank you.
You can clear this off.
Thank you.
All right, so last class, I told the other section and realized that we hadn't really talked about this, but there's so in linear algebra, like you spend some time inverting matrices. It's like, and in general, like if you can find a solution for x, then then the matrix has to be invertible. And just a quick. So if we have this problem, one way to solve it is that solve for A inverse, and now A inverse times A x equals A inverse times B. So x equals A inverse times that B. And that works. Like if you're doing it by hand, totally fine. But there's never a reason to solve for the inverse of a matrix and then do this calculation. So we're going through all this process of like LU decomposition and Gauss elimination and this pivot matrix and all this. The reason for that is that it's always more efficient to do LU decomposition and solve it that way with a forward-backward substitution than it is to solve for an inverse of a matrix. And there's a few different reasons for that. One of them is like in this first problem, we had this K matrix that it's like there's a lot of symmetry involved. It's called sparse when there's a lot of zeros in it. So sparse matrices that with a lot of symmetry, those are easy for a computer to solve and easy to work with. But if I try to invert it, np.linalg.inv of :(-1, :(-1. I take that nice like sparse, like lots of zeros and symmetry. It's still got most of the symmetry that's there, but now it's a completely dense matrix. And the bigger the matrix gets, it's always gonna, the inverse is almost always more dense than the original matrix. So one, you're storing a lot more values, and as you do math with those, you're going to introduce more error as you're doing it. The other reason is that it's just slower, like it's slower to solve for the inverse and save all the values. So like if we come down here and we'll start timing some things. Oops. If I create like a random 1000 by 1000 A matrix and a random B matrix, so just a fully dense A matrix with a whole bunch of right-hand side values, and time how long it takes to solve, just take linalg and solve it, which is basically Gauss elimination. Like in the background, it does some other checks, but for the most part, it's Gauss elimination. and take a second, versus, so that took like 25 milliseconds versus finding the inverse and then using that to solve the problem, where I get the exact same answer. Like it should be the same. It actually introduces some error, probably not enough to like write home about, but it does introduce some error. So it went from 25 milliseconds. What? Why is it slower? No, that's not right. Something went wrong. For the most part, it's always like 50% faster. So I don't know what happened. Yeah, so 12 versus 16. So it's always slower to solve for the inverse. Again, like we're engineers, like we're mechanical engineers. For the most part, we just want answers. Like we're not, you don't have to worry about this too much, but there's just as a quick, just to like be like relevant around like computer science and numerical methods people, like never take the inverse and then use that to solve problems. It's kind of wasting computer resources, and you're never using that inverse for anything else. Like the inverse is always getting you an answer, and there's better ways to get the answer. So quick public service announcement about numerical methods and linear algebra. It's always a better way than the inverse. That was this is another episode of the questions that nobody asked. But we could take a look at this. I saw some people kind of looking at this problem, because we had like so if we have like stress as a function of time, maybe it would help to actually put some labels on there. With these Prony series calculations, you're looking for like what's the magnitude of different time constants as this thing is decaying. So like we could look at this and just say, all right, it's one exponential decreasing curve, and that's one way to do it. So we could come in and say, np.exp of negative t over, what's the first one, 11? No, 1.78. So I could just look for like two coefficients. One is the time constant for 1.78 seconds, and then the other one is just some offset of like what is the initial stress at time 0. And there I don't capture, I capture all of the initial like fast decreasing stuff, but I don't capture any of the longer time constant. So it's like, all right, well, something more is happening. Let's keep adding some np.exp negative t over 11. now it's starting to look a little better, but it's still only capturing that first really like 11 seconds, right? It kind of makes sense. 11 to 12 seconds. So what are the other ones? 11, 53, 411. And by time I add all of those time constants, now I get a curve that's kind of describing everything even out to that 600-second decay. So it seems like the fit is working pretty well. One of the other things we're asked to do for this problem is try to increase the number of points that I'm evaluating along the way. So I have these coefficients like A. So 1.9, 3.3, 1, 2.3, and 30.6. So 30.6 is my initial stress, and all these other ones are the magnitudes of like those other exponential decays. So I have that. I can build a new like Z matrix, or I can write out the function again, right? Like I could just rewrite that function, or I could create a new Z matrix like this. I could just do it like this, like make a lambda function like that. Say like ZF is a lambda. So if I plug in any value of t, that'll give me. So if I said like ZF of 0, that's at time 0, it'll plug in time 0 times A, and it gives me, oh, no, nothing. Like that, maybe? Oh my god. So I have to give it an array. Even if it's an array with length 1. There we go. So if I give it array at time 0, then it tells me stress at time 0 was 39 megapascal versus time 100, kind of extrapolating my result. Now it's like 32.5 megapascal. Or I can give it a whole like Lin space, right? Yeah, go from 0 to 600. Now I've got like a nice smooth curve because I'm evaluating it 50 times instead of like 20 times or something. So it shows me what happens to my function in between those data points, which is kind of, sometimes that's really helpful, like especially if you're plotting like high order polynomials between points. It might look nice at the first glance, but then if you evaluate in between, you start seeing big jumps. But this stats models, I think I was showing like some of this. This is doing the same linear regression that we defined. So it's taking like that Z matrix, Z transpose Z, equals Z transpose S, like my right-hand side measured values. The only difference is that the model that the results that it gives you from there. Let's make a new thing here. I think it's summary. No. I thought it was summary. Yeah, there we go. So if you look at, you create like the ordinary least squares model from like measurements and that Z matrix, whatever function you're doing. Then you say results fit, so it's going to take that least squares, turn it into a regression model, and now it gives us every statistic you could want plus 10 other values that maybe you would never know what to do with. So the big ones that that usually people ask for are kind of like, what was your R squared value? The closer it is to 1, kind of the better. If it's 1, something's weird. Like that means that the fit, it went from a standard deviation of like 10 to 0. Like every data point went directly through your model. So something's a little weird if it's exactly 1. If it's like 99%, that means that things are going pretty well. Yeah, and then also like some stuff that we already knew about it. Like we had 22 measurements of stress. So number of degrees of freedom was 17. We had degree of freedom of the model was 4. Yeah, all sorts of good stuff there. Omnibus, probability of omnibus, skew kurtosis. Anyway, so that stats model is a nice way of like getting a little bit more information out of these like least squares regression fits. Same thing with like polyfit. Like if you're polyfit and polyval, stats models is a nice like more robust way of like getting all the information you need out of it. Cool. All right. Have a great weekend. I'll see you again on Monday. Enjoy Friday off. Thanks a lot.